How's it going, guys? In this video, we're going to be going over the rest of 6.2 notes. We're going to be talking about how to sketch a polynomial function graph in intercept form without using a calculator. So the first thing we're going to do is we're going to find and graph the solutions. The solutions are also known as the roots, the zeros, but they're really just your X intercepts. And to find them, what you'll do is you're going to figure out your factors, and you're going to set the factors equal to 0, and that will be your X intercepts. The second step we're going to do is that once we have our X intercepts, we need to know how the function is going to react at those X intercepts. If the exponent of a factor is even, then the graph will be tangent at that X intercept, or in other words, it'll bounce off of that X intercept. If the exponent of a factor is odd and is greater than or equal to 3, so for instance 3, 5, 7, 9, so on and so forth, the graph will have a change in concavity at that 0, and what that will look like, it's going to look like the y equals x cubed graph. It's going to cross it something like that. That little squiggle, we have two little concavities in the graph. It's going to look like that when crossing the x-intercept. And finally, if the exponent of the factor is 1, then the graph goes just straight through that 0. So once we have our x-intercepts, we know how the polynomial function will react at those x-intercepts. We're going to find and graph the y-intercept next by setting all the x's in the function equal to 0. Once we do that, we need to figure out kind of what the graph is going to look like, more or less. Or in other words, we need to know the starting and ending behaviors of the function. And we can do that by looking at the overall degree of the entire polynomial. And we're going to look at the sign of the first term and see if it's positive or negative. We're going to look at the leading coefficient, and we're going to see if the leading coefficient is positive or negative. So if we have an even degree with a positive coefficient, so for instance, we have y equals x squared. Y equals x squared, we know looks like this. It starts up and it ends up. So an even degree polynomial with a positive coefficient can look something like that. The important part is it starts up and it ends up. Then we have an even degree polynomial with a negative coefficient. We can think of this as y equals negative x squared. Y equals negative x squared is an even degree polynomial with a negative coefficient. That -1 right in front of the x squared is a negative leading coefficient. In this case, we're going to start down and we're going to end down because y equals negative x squared looks something like that. So the end behaviors of y equals negative x squared will be the exact same as every other negative coefficient even degree function. It will start down and it will end down. Something to pay attention to here is that all even degree polynomials will always start and end going the same way. If it starts up, it's going to end up, and if it starts down, it has to end down. All even degree polynomials will end the same way. That's because you cannot have an even degree polynomial having a range of all real numbers. If you have a starting and an ending, if they start and they end going different ways, you end up hitting every single y value. And an even degree polynomial, if you remember from the last video, an even degree polynomial will never have a range of all real numbers. All right, so for odd degree polynomials, if we have an odd degree polynomial with a positive coefficient, we can think y equals x cubed or y equals x. For y equals x cubed, this graph will look something like that. So that's a positive coefficient with an odd degree. So that starts down and it ends up. So it can look something like that. It doesn't really matter how many turns, turning points you have, whatever you want. As long as it starts down and it ends up, that's an odd degree polynomial. For an odd degree negative coefficient or negative polynomial, we can think of y equals negative x cubed, where it's just going to be the flip of the graph we just drew. That's not drawn very well, but the point is that it starts up and it ends down. So maybe something like that. Something to pay attention to here is that all odd degree polynomials will start and end going different ways. The starting and ending behaviors of odd degree polynomials have to go different ways because that's the only way you will be able to say that that polynomial has a range of all real numbers. So if it's going different ways, we can know that it's an odd degree polynomial. Let's go on to the next page and do an example. For number 1, we see we have 3 distinct factors. We have x plus 3, x plus 2 cubed, and x minus 1 squared. Each one of those is one distinct factor of the function, and each one will give us one x-intercept. For x plus 3, we're going to use the first one in blue. That one gives us an x-intercept. Don't know where that came up red, but for the first one that's in blue, that will give us an x-intercept of -3. Since if we set x plus 3 equal to 0, x has to be -3 for that to equal 0. Okay? For the second one, in green, x plus 2 cubed, that x plus 2 cubed will equal 0, and x equals -2. And lastly, for x minus 1 squared, x minus 1 squared will equal 0 when x equals 1. Right? For each one of these, you plug them back into that factor. The factor will give you 0. 1 minus 1 is 0. For the green, -2 plus 2 is 0. And for the blue, -3 plus 3 equals 0. And that's what we want. So we have our x-intercept. What we need to do now is we need to figure out how the graph will react at that x-intercept. So at x equals -3, what we're going to do is we're going to look at the factor, we're going to look at it by itself, and we're going to look at the exponent. The exponent is the number that's the factor is raised to. For x plus 3, we see we don't have anything here. If you don't have anything there, it's just raised to the first power. So x equals -3 is raised to the first power. The exponent of that factor is 1. If the exponent of the factor is 1, we go straight through that point. And then for the next one, we're going to look at the x-intercept x equals -2. We got the factor, we got the x-intercept of x equals -2 from the factor x plus 2 cubed. X plus 2 cubed is raised to the third power, right? You see that exponent of 3 right there. It's raised to the third power. If it's raised to the third power, we know it's going to be a concave change or change in concavity, whatever it is. That's what it is. Because it's raised to the third power and 3 is an odd number greater than or equal to 3. And lastly, we have the one in red. We have the x-intercept x equals -1. That's in red. And we see in the factor here, x minus 1 is raised to the second power. So that factor is raised to the second power. 2 is an even number. And we said in the previous slide that if the factor is raised to the second power, is raised to any even number, it's going to be tangent or it will bounce at that point. So what we're going to do now is we're going to graph the x-intercepts at x equals -3, or sorry, x equals -3, x equals -2, and x equals 1. That is all of our x-intercepts. So we have our x-intercepts. We know how the graph will react at those points. Now we need to know what our y-intercept is. To find our y-intercept, we're going to plug 0 in for x. So we get 0 plus 3, or just 0 plus 3, multiplied by 0 plus 2 squared, cubed, 0 plus 2 cubed, and 0 minus 1 squared. 0 plus 3 is just 3. 0 plus 2 is 2, and 2 raised to the third power is 8. 0 minus 1 is -1. -1 squared is 1. 3 times 8 times 1 gives us 24. So our y-intercept is at 24. So now we need to know what the degree of the whole function is. And we know what the degree of the whole function is by adding all the exponents of the factors. So we have 3 factors here, x plus 3, x plus 2 cubed, and x minus 1 squared. And the exponent of the first factor here, x plus 3, is 1. The exponent of the second factor, x plus 2, is 3, is raised to the third power. And the exponent of the last factor, x minus 1, is raised to the second power. So we have a squared, a cubed, and 1. 3 plus 2 plus 1 is 6. So the degree of the entire polynomial will be 6. Next, we need to know what the sign of the first term is. If we look at the function over here, we don't have a first term here, which means the first term is actually 1. If you don't have anything there, we assume the first term is 1, and 1 is a positive number. 1's a positive number, so the sign of the first term is positive. So we have an even degree positive polynomial. So another even degree positive polynomial that we know of is y equals x squared. And for y equals x squared, we know what it looks like. It looks like that. Not the best graph, but it looks something like that. It starts up and it ends up. That's the important part. So an even degree polynomial starts up and it ends up. So let's go ahead and graph it now. We have everything that we need, so we can actually do it. So we start up, and we're going to go down to -3. At -3, we go straight through it. And then x equals -2, we have a concavity change. So we're going to keep going. We go through it with a little, I don't know what to call it, little, two little curves increasing. We're going to go through our y-intercept. And at x equals 1, we're tangent to that point, which means we just bounce right off of it. And that's what our polynomial function will look like, more or less. The important thing here is that you know you're going through all your x-intercepts, you're going through your y-intercepts, you're reacting at those x-intercepts how the polynomial should, and your end behaviors and your starting behaviors are correct. That's what we're looking for here, okay? So let's go on and do number 2 as well. For number 2, we have p of x equals 3x times x plus 1 cubed times x minus 1. Here we still have 3 factors. We have x plus 1 cubed, and x minus 1. That 3 is technically just our first term. It's our coefficient of the whole polynomial, so it's not really part of our first factor. So let's go ahead and look at the first factor here. We have x by itself. X equals 0 when x equals 0. So our first x-intercept is x equals 0. We're going to look at our second factor now at x plus 1 cubed. X plus 1 cubed will equal 0 when x equals -1. We plug in -1 into that factor. -1 plus 1 is 0. 0 raised to the third power is just going to be 0. And lastly, for x minus 1 will equal 0 when x equals 1. So we have our 3 x-intercepts. Now what we're going to do is we're going to figure out how the polynomial will react at those intercepts. So x equals 0. We're going to look at the factor that we got that x equals 0 from, and we're going to see what that factor is raised to. We got x equals 0 from the factor x by itself. X is raised to the first power. So if it's raised to the first power, we go straight through that point. For x equals -1, we're going to look at the factor that we got that x-intercept from. We got that from x plus 1 cubed. X plus 1 cubed has an exponent of 3. And since 3 is an odd number greater than or equal to 3, that means we have a concavity change at that intercept, at the x-intercept. And lastly, for x equals 1, we're going to look at the factor we got x equals 1 from. We got it from x minus 1. X minus 1, that factor is raised to the first power. You see that because we have no coefficient, sorry, no exponent there. If you don't have an exponent there, it's just raised to the first power. So it's raised to the first power. And if it's raised to the first power, it is going to go straight through that point. So now we have our x-intercepts. We know what's going to happen at those x-intercepts. So what we need to do now is we're going to plot those x-intercepts, and then we're going to find our y-intercept. So we have x-intercepts at -1, at 0, and at 1. And for our y-intercept, we don't actually even have to find it, and that's because we have an x-intercept at 0. If you have an x-intercept at 0, that means we're going through the origin, and the origin is the only point that goes to the y-intercept and the x-intercept at the same time. So if we're going through our y-intercept at 0, 0. We're also going through the x-axis as well. So our y-intercept is at 0, 0. You could just plug in 0 as well. You get the same thing. But if you have an x-intercept at 0, your y-intercept will also be 0. So let's go ahead and just plug it in anyway and see what we get. So y equals 3 times 0, which is 0. 0 plus 1 is 1. 1 cubed is just 1. And 0 minus 1 is negative 1. 0 times 1 times negative 1 will just be 0. So our y-intercept, we could have figured that out just by looking at our x-intercepts. But if we solve for it anyway, we'll get the same thing. The y-intercept is at 0. Now for the degree of the whole function, we're going to add the exponents of each factor. The first factor is just x. X is raised to the first power. Then we have the factor x plus 1. That's raised to the third power. And we have, lastly, we have x minus 1. X minus 1 is raised to the first power as well. So we have 3 plus 1 plus 1. That gives us a degree of 5. Now we're going to look at the sign of the first term. In this problem, our first term is 3. 3 is a positive number. So the sign of the first term is positive. So we're going to graph a positive odd degree function. So we can look at f of x equals x to the third power. That's an odd degree positive polynomial or a function, whatever it is you're going to call it. It's odd and it's positive. And that function looks like this, more or less. And we see we start down and we end up. And every odd positive polynomial will be the same way. It will start down and it will end up. So now that we know what our starting behavior is, our ending behavior is, our x-intercept, our y-intercepts, and how we'll react to the x-intercepts, we can go ahead and graph our polynomial. So we start at the bottom, and at -1, we have a concavity change. So we'll go through it like that. At x equals 0, we're going straight through it. And at x equals 1, we're going straight through that point as well. So our graph will look more or less like this. For number 3, you guys go ahead and pause the video and try it yourself, and I'll pop up the answer, and you can double check yourself with mine. So this is what you should have done for example 3. Our x-intercepts, we get them from our factors. We have factor of x plus 2. The x-intercept of that will be -2. We have x minus 1. The x-intercept of that will be 1. And we have x plus 1. The x-intercept of that will be -1. Remember, we set each factor equal to 0. So each term that's underlined by a different color, that's one distinct factor. Set each one equal to 0 and solve for x. And that's how we get our x-intercepts. And for each factor that's underlined by a different color, that's one factor. We're going to look at the exponent of each one. X plus 2 is raised to the first power, so we're going to go through that x-intercept straight. X minus 1 is also raised to the first power. We're going through that point straight as well. And for x plus 1, that's raised to the first power. We're going to go straight through that point as well. So all three of them we're going through. We're going to go through it straight. For the y-intercept, we plug in 0 for x. We end up getting 2. So that's our y-intercept. If we add up all the degrees of the factors, we get 3. And the first term of this function is -1. -1 is a negative number. So the sign of the first term is a negative. So we have a negative odd degree polynomial. So for instance, that's very similar to y equals -x cubed. So it looks something like that. So the point is we're going to start up and we're going to end down. So our polynomial graph should look something like this. Okay? So that's the video for today, guys. Hopefully this helped.